Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at the field axioms. In this topic, we will introduce the 8 axioms for real numbers, or the 8 field axioms. We will observe that both reals and rationals satisfy these properties. However, we will also introduce other fields as well, just for interest. However, our focus ultimately will be to look at complex numbers. We're going to deduce properties or theorems based off of these axioms, and we will see that all the properties that you are familiar with and comfortable with for real numbers must therefore transfer also to complex numbers or any other field of interest. The significant algebraic properties or axioms of the reals include: the sum or product of two real numbers is still real. That is, they are closed under addition and multiplication. You sort of expect that. The same way that if you add two integers together, you don't get a rational number that's not also an integer. Addition and multiplication are commutative. That means that alpha plus beta equals beta plus alpha. It doesn't matter what order you add them in. Addition and multiplication are also associative. So it really doesn't matter if you add alpha plus beta and then add to the result gamma, or add alpha to the sum of beta plus gamma, and the same for multiplication. Finally, multiplication distributes over addition. And again, this is a property you're quite familiar with already. There are also identity and inverse axioms, and these include the fact that there's a zero. And zero can be added to any other real number, and the result is that other real number alpha. Also, every real number has an additive inverse. We denote it negative alpha, and if you add the additive inverse to that real number, you get 0. So 3.7 plus negative 3.7 is equal to 0. There's also a multiplicative identity. We call it 1. And 1 times alpha is always equal to alpha for all real numbers. And every non-zero real number has a multiplicative inverse, or the reciprocal of alpha, such that alpha times its reciprocal is equal to 1. So 3 times a third is equal to 1. Now, any set of numbers where we've defined an addition and a multiplication that satisfy all of these properties is said to be a field. So these are therefore called the field axioms, and you're familiar with these. You've used these often since elementary school. 0 plus 3 is equal to 3. 7 times 1 is equal to 1. An important concept, however, is that all the other properties of real numbers that you're familiar with can actually be deduced using only these 8 axioms. The rational numbers also form a field. The sum or product of two rational numbers is still going to be rational. You can't add or multiply two rational numbers and get, for example, root 2 or pi. All the other algebraic properties also hold. And, of course, the additive inverse of 9 over 4 is negative 9/4. The multiplicative inverse of 9 over 4 is 4/9. To calculate the multiplicative inverse, the numerator cannot be 0, because 0 over any non-zero integer is going to be equal to 0. Here's another interesting field. Consider all numbers of the form rational plus rational root 2. If I add two such numbers together, the result still is of the form rational plus rational root 2. If I multiply two such numbers together, I never get rational plus rational root 3. It's always going to end up being something of the form rational plus rational times root 2, just to expand the two out. There's an additive inverse. I can add negative 1 plus 3/2 root 2 onto the left-hand operand, and I get 0. I can also multiply 1 minus 3/2 root 2 by the expression on the right-hand side, and I get 1. Now you may be wondering, how did I get negative 2/7 minus 3/7 root 2? Well, you can already deduce this from secondary school. 1 over a radical can be simplified, or I can rationalize the denominator by multiplying by 1, where 1 is equal to the radical conjugate over the radical conjugate. Multiplying out the denominator, I get that equals to negative 7 halves, and then expanding, I get that the result is negative 2 sevenths minus 3 over 7 times root 2. Now, you might ask yourself, is it ever possible that rational plus rational times root 2 times its radical conjugate is equal to 0? Now, one field critical to cryptography are the integers modulo p, where p is a prime number. That is, the integers from 0 to p minus 1, where addition and multiplication are performed as per normal, but we only keep the remainder when the result is divided by p. So, for example, when p is equal to 5, we have the following two tables. You will notice that, for example, 3 plus 4 is equal to 7, but the remainder of 7 when divided by 5 is 2, so 3 plus 4 is equal to 2. Notice also that 2 plus 3 is equal to 5, but the remainder when 5 is divided by 5 is 0, therefore 2 plus 3 is equal to 0, so the additive inverse of 2 is 3, and 3 plus 2 is also equal to 0. Going over to multiplication, we note that 3 times 4 is equal to 12, but the remainder when 12 is divided by 5 is 2, so therefore 3 times 4 is equal to 2. Notice also that 2 times 3 is equal to 6, and 6 divided by 5 has a remainder of 1, therefore 2 times 3 is equal to 1, and 3 times 2 is equal to 1, and therefore the multiplicative inverse of 2 is 3, and vice versa. Specifically, notice also that 4 times 4 is equal to 16, which has a remainder of 1 when divided by 5, and therefore the multiplicative inverse of 4 is itself. Now, some common collections of numbers are not fields. Consider the integers greater than or equal to 0. All of the axioms are satisfied except for the existence of additive inverses. There is no positive real number such that if I add it to 3, it gives me 0. The integers are almost a field, but multiplicative inverses do not exist. For the most part, there is no integer n such that 3 times n is equal to 1. The irrationals by themselves are not a field because I can add two irrationals together, but the result is 0, which is not irrational. Similarly, I can multiply two irrationals together, but the result is 2, which is, again, not an irrational number. Previously, we considered the integers modulo p, where p was a prime number. What happens if we consider an n that is not prime and perform the same operations? For example, when n is equal to 6, we have the following two tables. It looks like for addition everything is okay. Every number has an additive inverse. But looking at multiplication, notice that, for example, there's no number which multiplied by 4 gives a value of 1. That is, 4 does not have a multiplicative inverse. You will also notice that 4 multiplied by 3 is 0. So 4 times a non-zero number is equal to 0. So consequently, the value n must be prime for this to be a field. From these axioms, we can deduce further theorems or properties. For example, the axiom says that alpha plus 0 is equal to alpha. Is 0 plus alpha equal to alpha as well? Well, yeah, it's reasonably straightforward, and you would expect that. All you use is the commutative property, and you get that 0 plus alpha is equal to alpha plus 0, which is, of course, from the axiom, equal to alpha. And because if A equals B and B equals C, it follows that A equals C, therefore 0 plus alpha is equal to alpha. Similarly, there is only one number that has the property of 0. Now, we're not going to go through this in detail, but we could assume that there are two different zero elements. Let's call them 0 and z. Let's assume both of them have the property that alpha plus that number is equal to alpha for all alpha. Well, if that's true, then that property must also be true for both 0 and z, and consequently we can show that if there are two objects that have the property of 0, then those two objects have to be the same. Easy enough. Here's another theorem. The multiplicative inverse of the multiplicative inverse of a number must be that number. How do we show that? Well, the multiplicative inverse of the reciprocal of alpha must satisfy the property that the reciprocal of alpha times that multiplicative inverse must equal 1. Well, at this point we can just multiply by both sides by alpha, and again by applying the axioms we see that yes, alpha must be equal to the inverse of the multiplicative inverse of alpha, and therefore the multiplicative inverse of the multiplicative inverse of alpha is equal to alpha. For example, the multiplicative inverse of 1.25 is 0.8, and the multiplicative inverse of 0.8 is 1.25. Now, why are we doing this? Well, what we want to see is that any set of numbers where we have an appropriately defined addition and multiplication that satisfies all 8 of these field axioms must therefore also satisfy all of the consequent theorems. That is, all of the properties of the real numbers that you're familiar with should also apply, and do apply, to complex numbers. Now, this notation here is going to be used throughout this class to say that A is by definition equal to B. So therefore, we can say that alpha minus beta is just a shorthand for saying alpha is added onto the additive inverse of beta. Similarly, alpha divided by beta, or alpha over beta, is just alpha times the multiplicative inverse of beta. Notice therefore that, as you would expect, alpha minus beta is not equal to beta minus alpha, and alpha divided by beta is not generally equal to beta divided by alpha. We can also define a sum without parentheses as being the sum of the first two entries plus subsequent entries, and the same for multiplication. Also, if there's no chance for ambiguity, we can get rid of the dot. So juxtaposition represents multiplication. We can also define integer exponentiation. Alpha to the 0 for any alpha is defined as the multiplicative identity, or 1. For n greater than 0, alpha to the 7 is equal to alpha times alpha to the 6. And for n less than 0, alpha to the negative 5 is the reciprocal of alpha times alpha to the negative 4. So all these definitions and rules, together with BEDMAS, allow us to simplify our expressions. We evaluate everything inside brackets first. Then we perform any exponentiations. Then we perform divisions and multiplications left to right. And finally, we perform additions and subtractions, again, left to right. So here's another question. Is the multiplicative inverse of alpha beta equal to the product of the two multiplicative inverses when neither of those values are 0? Well, we can use the definition of a multiplicative inverse to start with, and then multiply both sides by the multiplicative inverse of alpha. This, together with a few algebraic manipulations based on the 8 axioms, allows us to get to the expression at the end, and then, given that expression end, we can multiply both sides of that by the multiplicative inverse of beta to get the following. And yes, we do actually see that the multiplicative inverse of the product is equal to the product of the multiplicative inverses. Therefore, we get our result. That is, the inverse of a product is the product of the inverses. However, one thing that's very important, when we were doing this derivation, if you go back and look carefully, you will notice that we actually depended on the property that multiplication is commutative. That is, alpha times beta is equal to beta times alpha. Now here's a question you probably saw in secondary school. Is the expression on the left-hand side equal to the expression on the right-hand side? Well, in secondary school, you probably did the following. You multiplied by 1. That is, you just multiplied both numerator and denominator by alpha beta. You then expanded both sides, divided alpha on each side, and you probably just immediately applied commutativity to just say that the denominator is alpha plus beta, and we're done. Yes, it's true. We could also prove this with the field axioms, but first we have to write it in terms of multiplicative inverses. Great. And then we can carry on as follows. At every single step here, I am applying either a definition or one of the axioms. And we get down to the bottom and we notice that thus, using these axioms, we do know that yes, indeed, the reciprocal of the sum of the reciprocals is equal to that expression on the right-hand side. This is true for all fields, the reals, the rationals, and any other set of numbers with two operations that satisfy the field axioms. Specifically, all of this also still applies for complex numbers. Thus, in the next few topics, we're going to introduce complex numbers. We're going to see that complex numbers are a field, just like the reals and the rational numbers. Therefore, all the properties you're familiar with real numbers and rational numbers, they apply to complex numbers too. This is going to make your undergraduate career a lot easier if you remember this very simple fact about how complex numbers will work. Now, the question is, what do you prefer? Do you prefer the approach you saw in high school, such as on the left-hand side, or the axiomatic approach on the right-hand side? It doesn't take much to realize that you probably prefer what's happening on the left-hand side, and that's what you will need in this class. You will never be asked to derive the proof using the axiomatic approach for real numbers, or the fields in general. You're familiar with these properties, you're going to use them, and when you get to complex numbers, you're going to use those same properties, and you should be using them as if you were using them with real numbers. Now, important, the property we just showed is true only because the multiplication of real numbers is commutative. For matrices, we're going to see that in general this may not actually be true. Why is that? Because for matrices, matrix multiplication is not necessarily commutative. Now, if you don't know what matrix multiplication is, don't worry about it. We'll see a lot of that later. But the takeaway is, don't assume that matrices work exactly the same way that real numbers work. Now, let's do a quick review. Colloquially, you already know the field axioms. You know that the sum or product of two real numbers is a real number. You also know that if you have n real numbers, you can add them in any order that you want, and you're always going to get the same result. The same goes for multiplication. You know that multiplication distributes over addition. You know that 0 can be added to any real number, and that leaves that number unchanged. Similarly, multiplying any real number by 1 leaves that number unchanged. Every single real number has an additive inverse, and every non-zero number has a reciprocal. Thus, all the properties you know about the real numbers can actually be derived from this very small set of only 8 specific properties or axioms of the real number. And all the additional properties you know about the real numbers also apply to any other system that satisfies these same axioms. The complex numbers satisfy these axioms. If any system does not satisfy even one of these axioms, then none of the established theorems or subsequent properties may necessarily apply. For example, we will see vectors. With vectors, we will see that we cannot multiply two vectors together. Similarly, square matrices can be multiplied, but it is not true that matrix multiplication is commutative. So in this topic, we introduced the axioms for fields. There are 8 specific properties or axioms, and the real numbers and the rational numbers satisfy all these properties. From these, we can deduce a number of theorems, and one thing that is nice about these results is that they must apply to all systems satisfying those axioms. All the properties will hold for reals also hold for complex numbers. You should be, and hopefully at the end of this course, you will be as comfortable with real complex numbers as you currently are with real numbers. Here are the references, acknowledgement, the colophon, and a standard disclaimer. Thank you for your time.